Okay, flush with success from packaging soup and fencing pastures, we're on our way home from the bank, you know, making money as so many calculus students do. And on our way back to our house, imagine that a math teacher bursts through a wall like Kool-Aid Man and insists, "No, you need to do this for the love of the game." So they end up presenting us with this particular problem. So lastly, we want to find a point on a parabola defined by y equals x squared right here that is as close as possible to another point not on the parabola, 6, 0. So and they just won't leave us alone. We're walking down the sidewalk and they just keep hounding us about how to do this problem and how important it is to do it for the purity of the mathematics. So we want to get them off our backs, right? So looking at this, we're going to execute our 4-step procedure one last time. The catch is this may be the trickiest time yet in terms of identifying that objective function, which, as I've stressed, is critical to making sure that you end up in the right place when it's all said and done. So unlike a lot of our previous examples, we don't have minimize or maximize floating around inside the description to point us directly at this is the thing that we need. The catch here is we're told we want to be as close as possible to this point right here. So if you can imagine from our picture, we want to be as close as possible there for this random point that I sketched and labeled XY. Closest in this instance is going to mean we want that dotted line segment I just drew in to be as short as possible. We're trying to minimize the distance. That's our plan. So one more time, we're tracking down a minimum. And you may notice from looking at the handout where this particular example comes up, we give you a hint where we say minimize the square of the distance. If you don't remember what we call the Euclidean distance formula, that's okay. I'll give you sort of a quick and dirty version of what it looks like here. So the square of that distance is going to look like this. X coordinate difference, quantity squared. Y coordinate difference, quantity squared. The true formula has a square root floating around on it, but we can actually get around needing the square root because looking ahead a bit at our calculus process, when we take a derivative, that's going to require us to use the chain rule, right? Right. When we use the chain rule, we end up carrying around that exact same square root term. So the chain rule part ends up forcing us to take a look at the derivative of what's underneath that square root, which is this stuff right here. So I'm just going to, focus on the square and not have to carry around a bunch of radicals because, again, as Pikachu is so prone to point out to me, I'm short on board space. So there's our objective function. It looks like that. We don't have an awful lot to do in this instance. We have very few tools to work with because we don't have any like real-world geometric applications in question. We still got two variables. That's bad. Do we have a way to get it down to a single variable? We do. That's good. So as it turns out, it's already sitting right here, and you may have already jumped to this if you're on the ball. So any point on this parabola has to satisfy that equation, y equals x squared. That means I can replace this y with x squared. So I don't touch the first piece. It's still x minus 6, pardon my handwriting, squared, plus x squared squared, because subtracting 0 isn't going to change anything. And now my picture needs to leave, so I've got a little more space to work with. So, I mean, the teacher drew it up there for us anyway. We don't want to have to deal with it, right? So force of habit, I'm going to write this. It's going to end up as a polynomial. I like to write my exponents in descending order. So x squared squared gives me an x to the fourth. I bust out my buddy the FOIL algorithm to handle this x minus 6 quantity squared. And I'll get that guy right there. So we have x to the fourth plus x squared minus 12x plus 36. Again, it's a polynomial. We like taking derivatives of polynomials. We're in hopefully a comfort zone here. So tracking down critical numbers means we need a derivative, and then we're going to figure out where either that derivative is 0 or the derivative is undefined. So power rule comes in to save our bacon again. We have 4x cubed. The derivative of x squared is 2x We've got minus 12 coming out of that guy, but 36, he's a constant. He goes poof when we hit him with a derivative, so he's gone. This is a polynomial. It's defined for all values of x, so we don't need to worry about any undefined monkey business. We set this thing equal to 0. Now, in all of our examples so far, we've done some algebra at this point to figure out what x equals. Put on the brakes. Don't do that here. You're gonna end up, kind of in pain, because trying to solve this cubic for x is not something I would generally expect you to do by hand. Instead, we would pop this thing into our calculator, see where this cubic polynomial crosses the x-axis, execute our 0 command, and see where it happens. If you like, you can also use Newton's method. You don't have to, but it would make me smile. I'd feel all warm and fuzzy inside. Anyway, so when I cranked this guy out, I got, oops, that is not what I got. I did not get 36. I got 1.32696, accurate to 5 decimal places. So, all right. So that's our only place that this thing ends up crossing the x-axis. So we've only got one candidate. This is probably not surprising at this point. Most of our examples, we've only ended up with one candidate. So again, we want to check and make sure that we've got a minimum. We don't want this silly professor who blew through a wall, complaining that we ended up maximizing distance instead. Step the fourth. This time around, we can't really cut this thing off. We've got, a true full-on number line in this instance, because we could theoretically have an x value way back over here. I mean, common sense kind of tells us that it's not going to work, but, so we got that guy as our one tick mark, and we need to check what our derivative signs are on each side of this thing. Good news. We can even pick something easier than 1 for once. We can plug 0 into this thing, because 0 is off to the left of our candidate point. Yeah, that's going to give me negative 12 when I feed in 0 for x, so definitely negative. Again, plug in a million, just, for the sake of it. Gymongous, less gymongous, but still big, minus 12. Yeah, that's going to be positive, right? So, again, that is what we want to see out of the minimum. We were dropping, we flattened out, we started climbing again. That is exactly what we want to see out of the minimum. So we minimize our objective function f, and at the same time, we're going to end up minimizing the distance, which is what this math teacher guy wanted out of us. So and then the corresponding y value you can get by squaring this guy. I actually didn't remember to do that before I wrote this. So I'll leave that to you to work out what the corresponding y coordinate would be. It's not going to be terribly challenging. We've done all of the heavy lifting at this stage. So that's optimization. We've seen 4 different examples of this guy in action at this point. I have tasked you with taking a look at a couple more before we move on to a new chapter of materials. So look forward to that. In the next video, I will touch base with you very shortly. Actually, I have no idea how quick it's going to be, because I have no idea how fast you're going to hit play on that next video. Also, I feel this strange compulsion in my mind that I feel like I have to ask that you like, share, subscribe, and hit the bell. You don't really need to do any of that. I just feel compelled to say it.